This example comes out of section 3.5, related rates. In general, I'd say that teaching related rates is easiest through example, which is true of a lot of math, but just showing you how to do a problem or two and then making you do more and more of it on your own. But in general, there are some techniques or some strategies for problem solving that will be useful here. First of all, step one is always going to be try to come up with some kind of a diagram. And sometimes it'll be given to you in the question. So in that case, obviously step one will be done. Step two, you need to relate the variables. So some kind of equation to relate. And the variables might be x and y, they might be radius and height, they might be volume, and it depends what the question's about. Step three, we take the derivative with respect to time. And again, I'll show you that with real examples. It kind of involves using the chain rule in a way. Step four, we then substitute values. And notice that comes after you take the derivative. That's probably the most common mistake in related rates problems, is to start substituting values in too early before you've taken the derivative. And then step five, naturally, any word problem, answer the question. And it seems like a silly thing to say, but often people do a whole bunch of beautiful math, get to the end of what they think is they're done, but they haven't actually answered what was asked. So let's look at this first word problem example. The question goes like this: a spherical snowball is melting so that the volume is decreasing at 2 centimeters cubed per minute. At what rate is the radius changing when the radius is 10? So, the picture is fairly simple. It's a sphere. You can't draw a sphere very well in 2 dimensions, but we have radius and volume are the two kind of values we're interested in. The volume of a sphere, and you have this on a formula sheet. I don't really expect you to memorize, but you will probably use it enough that you'll get to know that the volume of a sphere is 4/3 pi r cubed. Perfect situation, because we have dV by dt. The change of volume, change in time, is negative 2 centimeters cubed per minute, but it's decreasing, which is what makes it negative. And we're looking for dr by dt, which we don't have, but when we take the derivative, that is going to be one of the things we end up with. So when we take the derivative of this, we say, well, dV by dt equals 4/3 pi times 3r squared dr by dt. So every single variable that you differentiate, you end up with this dV by dt, dr by dt. If there were x's and y's, we'd have dx by dt, dy by dt. Now it really does come down to straight substitution of what values do we have. What am I putting in here? Well, dV by dt is negative 2. Over here we've got 4. Notice that those 3's cancel out, so I don't really need to do both of those. 4 times pi times r squared. Well, r is 10, so 10 squared times dr by dt. Notice I didn't substitute in any of these values until after I took the derivative, and that is key. Substitute the values comes after taking the derivative in the steps. So now it's just getting these numbers, and if the question asks for nearest tenth or something, I could use decimals. If not, I'll just use exact values. 10 squared is 100, so I've got 400 pi times dr by dt equals negative 2, so negative 2 over 400 pi, which I could reduce, I suppose, to negative 1 over 200 pi, is equal to the dr by dt. What that means is that the radius is changing at a negative rate, which means that it's shrinking. So shrinking at radius shrinking at 1 over 200th pi centimeters per minute. Not a very big number. If you change that to decimals, it's quite small, but it makes sense given the situation that the radius is going to decrease a little bit and that'll cause the volume to actually decrease a bit more, which is the answer of 2. So negative 1 over 200 pi is the answer to this question. So we've done the 5 steps as I said above.